Hello everyone. Today we start discussing viewing transformations, and we will start our discussion of viewing transformation by looking at parallel projections. So in general, when we see in the world, we work with a perspective projection. So in that case, if we have an object in the world, right, and we have a camera center. So here is the camera center, and the camera center is at some finite distance from the object. Then if I join the camera center with points on my object, so for example here I have joined the camera center with points on the object, and that gives me these rays which are known as projectors, and the points at which the projectors intersect the image plane, we get the images of respective points. So for example, if this is a point in 3D, then the point where the projector intersects the image plane, we get the image of this point. Okay, so this is perspective projection because the projectors, they converge at the camera center. Okay, and the camera center, or as we also call it, the center of projection, is at a finite distance from the object, right? In contrast, for parallel projection, the projectors are all parallel to each other, so they do not appear to converge at any point. Okay, the imaging process is still the same. If you take a point in the world, right, point on an object in the world, and you figure out where the corresponding projector intersects the image plane, you get the image point, okay, corresponding to a world point. So the imaging process is the same, however the projectors are now all parallel to each other. So projectors are all parallel to each other. But in such a case, can you tell me where is the center of projection? Because the center of projection earlier was at a point which was at a finite distance from the object, but now that the projectors are all parallel to each other, the center of projection is driven to infinity, right? So the center of projection is no longer at a point that is at a finite distance from our world. Okay, so in the perfect parallel projection case, we have a number of constraints going for us. Okay, and this simplest parallel projection that we have is known as an orthographic projection. So what is so special about the orthographic projection? Well, we have a number of constraints here. Since it is a parallel projection, so the projectors, right, the projectors are parallel to each other. Okay, so projectors are parallel to each other. Then, of course, by virtue of this, camera center is at infinity. So these two are like similar points. Then the second point is that the projectors are perpendicular to the image plane. Okay, and the third point is that the object is aligned to the axial planes. Okay, so what does that mean? It means that the front face of the object, so for example, this is the front face of the object, this and that, these are parallel to the XY plane. The top face of the object is parallel to the XZ plane, and the side face of the object is parallel to the YZ plane. Okay, so XZ X, Y, Y, Z. So this is the object is nicely aligned to the axial planes, right? And that allows us to get these different orthographic projections on the X, Y, X, Z and Y, Z planes, which we know as the top view, front view and side view. I'm sure you have seen these in engineering drawing. And these are the projections on the X is equal to 0, Y is equal to 0 and Z is equal to 0 plane. On these planes, when you take a projection, for example, when you see the front face of the object on the XY plane, which is a Z is equal to 0 plane, we get the true lengths of lines that lie in this plane or in a plane parallel to this plane. Okay, so this length, for example, will be the actual length of between the corresponding points in the world, right? So how does this work mathematically? Well, the projection matrix for the Z is equal to 0 plane looks like the following. It is identity everywhere except for the value at the Z coordinate, which we force to 0. So everything else stays the same. So you take a point and you multiply with this. The X and Y coordinates will not change. The homogeneous coordinate will not change, but the Z coordinate will go to 0. So this is very simple. So the good thing about the orthographic projection is that it is very simple, right, to apply. You also get these nice true sizes and shapes on the planes of projection. However, the bad thing is that you only see one side of the object. So you only see the front side or the top view or the side view and so on, right? So that does not really tell you anything about the 3D shape of the object, because the object you can only see in one of the profile or one of these views that are aligned to the axial planes. So the reason projections were studied was because people wanted to represent the 3D world on 2D pieces of paper. Okay, and now because we are doing computer graphics, we want to represent the 3D world on the 2D screen. So that is why projections are interesting, because they allow us to map something that is in 3 dimensions to something that is in 2 dimensions, right? So from the 3D Euclidean world to the 2D Euclidean plane. So of course, when these methods were developed, they were developed for drawing on paper. So people started doing orthographic projections, and they are okay for engineering drawings, but really when you want to see an object in 3D, you need to get a better sense of the 3D shape of the object, and that you cannot get just by looking at the orthographic projections. Okay, so I'm sure you have heard of the term isometric view in engineering drawing, right? So you often use the orthographic projections to build what is known as an isometric view of a 3D machine part or a 3D shape, right? So how does that happen? So that is what we call as an axonometric projection. And in axonometric projection, we are going to relax one of these 3 constraints, right? So we had these 3 constraints, 1, 2, and 3, and we are going to relax the 3rd constraint here. We are no longer going to have the object aligned to the axial planes. Okay, so we are going to first transform the object and then project using an orthographic projection. Okay, such that multiple faces of the object become visible. This allows us to see the 3D object better in the projection, right, or on the 2D plane. Okay, so we have to characterize axonometric projection just like we did for orthographic projection. We said we have a top view, front view, side view. So what are the kinds of axonometric projections which are there? So to do that, let us construct this matrix U by stacking the unit vectors along X, Y, and Z axis. So this is the unit vector along x, this is the unit vector along y, and this is the unit vector along z. So this is like a pseudo matrix. We have put together all these unit vectors to form a matrix, and to this I am applying, say, a axonometric projection T, right? Now under the effect of this projection, x prime is going to go to xx prime, so x hat is going to xx prime, yx prime 0 1, y hat is going to xy prime, yy prime 0 1, and similarly z hat is going to xz prime, yz prime 0 1. Okay, so this is the projected form of these unit vectors under the action of T, right? Now what do we say? We say that if this was the action of T, that it mapped the unit vectors to those vectors, then we can compute the change in length of these vectors. Okay, so the length of the new vector is xx prime squared plus yx prime squared square root, right? And of course the length of the original vector was 1. So the ratio of the new length to the original length is known as a foreshortening ratio. Okay, so we compute the foreshortening ratios along x, y, and z, right? And we will use these values to characterize axonometric projections. So what do? We say that if the foreshortening ratios in all the three axes is different, right? That means we get different foreshortenings along the x-axis, different foreshortenings along the y-axis, and different foreshortening along the z-axis. Then we get what is known as a trimetric projection. If fx is equal to fz, or if fx is equal to fy, or if fy is equal to fz, if any two foreshortenings are the same, then we get what is known as the dimetric projection. Okay, and if all three foreshortening ratios are the same, then we get what is known as the isometric projection. So this is what you have seen, where fx is equal to fy is equal to fz, right? So this is how we characterize axonometric projections. Remember, how did we get to axonometric projections? By relaxing the condition that the object faces must be aligned to the axial planes. Okay, we are still taking the projection on the z is equal to 0 plane. For example, in this T matrix, if you see, the z coordinates are all 0. However, we have first transformed the object. So it is worthwhile to figure out how have we transformed the object. So if, for example, this was a side view of a cube, right? And if this is the y-axis and that is the x-axis, so let us say this is y and this is x. So if I rotate about the y-axis, yes, if I rotate about the y-axis, then I might see a view of the cube that looks like this. Okay, so this is the rotated cube. I have rotated the cube slightly about the y-axis. So let's say I do a rotation that is like this, and that gives me this second view. And now I apply another transformation where I rotate about the x-axis, say by doing a rotation like that, and now the view of the cube is going to become something like this. Okay, where continue to have the y-axis. Okay, so you can see that this was the orthographic view, and this is a axonometric view. Okay, so how did we go from here to there? We applied a ry and we applied a rx. Okay, this we did by theta and this we did by phi. Okay, so this is what we say. We are applying a ry to the object first, then we are applying a rx, a rotation about x, then we are doing a projection on the z is equal to 0 plane. So how does this matrix look like? If you So if we construct this matrix, then you will find that the matrix T looks like the following, right? So this is just a product of Ry phi and Rx theta. And to study the effect of this transformation, we apply it to the same U as earlier, which has the three unit vectors stacked up, and the transformed U that we get has these three columns, which are, so the vectors x hat, y hat, z hat transform to these three vectors under the action of this T. Now we can compute the foreshortening ratios for this this transformation, and fx square, fy square, fz square now get these values, right? So now if I apply the additional constraint that all the three foreshortening ratios have to be equal, then we can solve for theta and phi, and we get that phi is plus minus 45 degrees and theta is 35.26 degrees. So for an isometric projection, right, we apply the isometric constraint that all the three foreshortening ratios are equal, and we get values for theta and phi. Okay, so I hope now you have a sense of what happened when you moved from orthographic projections to axonometric projections, right? You basically rotated the object twice so that you could see more sides of that object. Okay, so we started with orthographic projections where we had put three constraints on the object, right? Parallel projectors, center of projection at infinity was the first. The second one was that the projectors are perpendicular to the image plane, and the third one was that the faces of the object are aligned to the axial planes. We took away the third constraint and we got axonometric projections. Okay, now we are going to relax one more constraint. This is the second one. So we are going to say that the projectors need not be perpendicular to the image plane anymore. They are still parallel to each other. The center of projection is still at infinity, but the projectors need not be perpendicular to the image plane. Such a projection is called an oblique projection. Okay, because the projectors are hitting the image plane obliquely, right? Any length on the object that is on a plane parallel to the plane of projection, we will see its true shape and size. Okay, so keeping these points in mind, let us now characterize the kinds of oblique projection. So if you look at a point P in the world, right, and if you were projecting this point on the plane z is equal to 0 plane, so let us say this is the z is equal to 0 plane, okay, and if you were projecting this using the orthographic projection, say you would have got P prime, okay. So P to P prime, the only thing that has changed is that Z has gone to 0, X and Y are the same. So this projector is perpendicular to the image plane. However, for the oblique projection, the projector is no longer perpendicular to the image plane, and you get this new projector, and instead of getting the point P prime as the image, you will get the point P double prime, whose coordinates will be some XP and YP. Okay. Now assume that the oblique projector, this projector, makes an angle alpha with the plane, right? And the distance between the orthographic projected point and the oblique projected point is given by L, and this angle on the plane, so this is basically the angle that this vector makes, P prime P double prime with the x-axis, is beta. Okay, so given alpha and beta, right, we can characterize the oblique projection. How can we do that? So we say that tan alpha is Z by L. So you can easily see that Z is the distance of this point from the plane, right? So because it's this is the third coordinate, and this is L. This angle here is 90 degrees. Right, and this angle is alpha, therefore tan alpha is Z by L, or L is Z cot alpha. So you know Z. If I give you alpha, you can compute L. Fine. Then once you know L and I give you beta, then x plus L cos beta is xp and y plus L sin beta is yp. Okay. Now I will leave it up to you to construct a matrix that does the following, right? Given point xyz1, it computes xp yp 0 1 as this. Okay, and you can assume that alpha and beta are known to you, right? So are there different kinds of oblique projection depending upon the values of alpha and beta? Yes, they are. So if you typically choose alpha is equal to 45 degrees, we get what is known as the Cavalier projection, and in such a projection you can prove that lines perpendicular to the projection plane are not foreshortened. Okay, this is kind of easy to see because if alpha is 45, then L will turn out to be equal to Z. Yes, because these two sides will be the same. So the lines perpendicular to the projection will not be foreshortened. Another kind of oblique projection is when cot alpha is half and we get what are known as cabinet projections. Here lines perpendicular to the projection plane are foreshortened by half. Okay, and the beta value typically is held at 30 degrees or 45 degrees. Okay, so you have these are the most common beta values. Where oblique projections was used, so just like orthographic and axonometric projections are used in engineering drawing, oblique projections were frequently used when people made drawings of furniture, or oblique projections were also used in early arcade style video games. So if you have seen games like Street Fighter or Contra or the first Super Mario Brothers, right? When perspective projection was not completely implemented or too expensive to compute, people would compute oblique projections, and the characteristic of oblique projections would be these side scroller games where you would just get these buildings, right, which would look something like, so you would just get a cityscape where there would be various buildings drawn like this, and you would have a character here, and all this character would do was move here and the screen would scroll to the side, and perhaps you would get some enemies coming from this side, and they would have a fighting match or whatever, right? So these the background here was drawn using oblique projection frequently. Okay, so that is all that I want to talk to you about parallel projections, right? So we have seen three kinds of parallel projections, right? And in the next part of this lecture, we will start talking about perspective projection, where we will relax the final constraint that we have on parallel projections, that the projectors are parallel. Once the projector ceases to be parallel, the camera center comes to a finite point or a point at finite distance from the world, and we get perspective projections. Okay, so thank you.